Hey everybody, today we have a logarithmic problem that has a variable base b, and the we're supposed to find that base b. Okay, now these two numbers are fairly clear. I mean, this is like 11 squared, this is 9 squared. What about this number? How this is kind of four-digit number, it's kind of big, so it might be nice to analyze that a little further. Now, it's clearly divisible by 2. It's clearly divisible by 2, but what about other? It's not divisible by 5. It's not divisible by 3 because of the sum of the digits. But we can show that it's divisible by 11 by just doing this maybe sort of obscure result. This is the 10 squared position. And so what you can do is you can write this. There's an alternating digits test. And so you can write the sum of the alternating digits and see what you get here. So what we have is minus 1. This is in the 10 cube position, and 10, it alternates because of the statement that I think it goes 10 to the n is congruent to negative 1. Okay, which takes a little bit of proof, but it gives us a basis for a divisibility test by 11. Okay, and so that's what's going on with this odd and even powers. There's a sign alternation going on right here. Okay, now so since this is the 1 times 10 to the cubed, you have a minus 1 here. This is 9 times 10 squared, so you have a 9 here, and then you alternate. And what do we end up with here, folks? Plus 6. Okay, so that is equal to, or no, wait, this is minus 3 plus 6. We got it right? Yeah, and so that's 4. 15 equals to 11, right? And so this is a multiple of 11. That means this object is divisible by 11, okay? And it turns out this number is equal to 2 to the 4th times 11 squared. So again, y'all, I'm taking the time to show you this because, did I get this right? This is minus 4, 15. Yeah, that's equal to 11, right? Okay, now, so this factorization is going to prove useful because logarithms are effectively exponents, all right? For every logarithmic statement, there's a corresponding exponential statement. And so we're given that these two logarithmic expressions are equal to each other. And so that means they're both equal to the same exponent e. Okay, so this is just the definition of logarithms. Nothing to do with change of base. It's just the definition of a logarithm. All right. Now, so all of this stuff just follows. Here's your logarithmic statement. Here's your exponential statement. All right. Now, what we do here is just do some fairly simple algebra on this. We divide these two equalities, all right, and you get this statement right down here. Now, what happens right here is that we get, let's see, what is this? We're going to get, do we have b to the e canceling? Yes. So we have 6 to the e, all right, 6 raised to the e power is equal to, and let's write this. Let's go ahead and write down, what was it again? 2 to the 4th times 11 squared. So we have 2 to the 4th times 11 squared. See, this prime factorization to me is very, very useful. It's kind of a computation reducing in many regards. And so what you have here, what you still have 11 squared, right? Okay, and 11 squared over 3 to the 4th. Okay, but notice how the 11 squareds cancel out, and this will invert and multiply, and so this is equal to 2 times 3. This is fairly, I mean, I love this stuff. 2 times 3 raised to the 4th power, right? But what is that? That's the 6 that you see on this side, right? So all of this right here implies that e has to equal to 4. Our exponent is 4. Now what are we going to do with that? Well, we know that if e is equal to 4, we have this statement right here. So let's just come over here and write this. We would have b. Remember, we are trying to find b, right? So we have b to the 4th is equal to the cube root of 11. Slightly tricky. Raised to the fourth power, right? Over, what do we got here? B to the fourth. And then this would be also 3 to the fourth right here, right? So you can see just by inspection that B, if you take the fourth roots of both sides, you don't have to do inspection if you don't want, but it's pretty evident. When you lose the fourth powers here, you get B is equal to the square root of 11 over 3, which is our solution. So it's an irrational base that's slightly bigger than 1, which is sort of important. Once the base gets less than 1, I think you start getting negative exponents, right? And so you have to, that's a concern. It wouldn't be a deal breaker on this particular problem, actually. But in any event, that is our solution. B is equal to the square root of 11 over 3. So kind of a non-standard problem. Most of the competition problems don't do this kind of stuff. Usually you have some nice clean base, like an integer, a small single-digit positive integer. They keep it fairly simple, But this one was composed to have a irrational base. Okay, so that's that. And y'all, this was sort of similar to a Canadian math competition problem back in 1996, worked on Michael Penn's channel. This one's, I think his involved a square root in here somewhere. But here we have an integer quotient, and then this is a rational number, and this is an integer. But the base is actually the square root of 11 over 3. All right, I'm just checking the work here. Looks like I got everything right. Okay, thanks for viewing.